Hello, our viewers. Previously, we have tried to discuss about work concepts. We have defined work vectorially. We have also defined work as a dot product of force and displacement. And at last, we have also listed some types of constant force. Work done might be performed by constant force, or it might be performed by variable force. So among the common constant force, we have tried to list out applied external force, frictional force, and gravitational force. So today we'll try to see about work done by those forces. First, let's try to see about work done by the external applied force. If you have external applied force, which is constant force, let's take a box, might be here. Let's say force F is applied on it at an angle of theta. It might be displaced a distance of s. So the work done by the applied force is determined as work is equals to force dot s, or F times s cosine of theta. This was what we have already discussed in our previous lesson. We have tried to solve an example or two examples of having constant force. So you should have to recall that. Now, let's try to find the work done by frictional force. Students, what do you mean by frictional force? Let's try to find the work done or performed by frictional force. What is frictional force? How do we find frictional force? Well, frictional force is a force which is always oppose a motion of a given object due to the roughness at the contact surface. Therefore, if we take a given object, it might be a box again, if we exert horizontal force, it can be horizontal or at some angle, this is external applied force. This is an applied force. At the contact surface, due to the roughness, we do have a frictional force. And frictional force is always acting oppositely to the contact, to the objects, to the motion of the direction of the object. Therefore, this is frictional force. Frictional force. Here, the object is moving. It's not along the frictional force. Rather, it moves or displaces along the applied force. Now look, when we apply the expression of work is equals to Fs cosine of theta, where theta is the angle between the force and the displacement. Now look, what is the angle between the force? Which force? It's not the applied force. Rather, it is the frictional force. So the direction, the angle between the force, the frictional force, and the displacement is 180 degree. This is 180 degree. The frictional force is applied or acted in this direction, whereas the object is moving oppositely to this direction. Force and displacement are at 180 degree. Now, if you substitute here, work is equals to the force is frictional force, the displacement s times cosine of 180 degree. So cosine of 180 degree gives us -1 or -1. This is negative. Therefore, the result becomes work done by frictional force is equals to the negative of frictional force times displacement s. This is how we determine work done by frictional force. Students, do you remember that frictional force only affected by normal force? I hope you do so. frictional force is directly proportional only to the normal force. And the mathematical expression of frictional force is coefficient of friction, mu, times normal force, where mu represents the type of the material at the contact surface. Therefore, there are two factors are the type of the material or contact surface, and the normal force are the factors which affect frictional force. So keep this in your mind. The second type of force, constant force, is frictional force. Work done by frictional force can be determined like this. The third type of contact force is gravitational force. How do we determine the work done by gravitational force? So let's try to see that. Work done by gravitational force. Well, gravitational force, work done by gravity, like this. We can have such subscribe. Work done by frictional force, we can have work done by frictional force. We can have work done by the applied force as W and F. We can put it to distinguish. Therefore, work done by gravitational force is either along the direction of gravity or opposite to the direction of gravity. Therefore, let's take a given object might be moving from a given position or elevation. Let it be here. We have point A or 1, height A. This is elevation A, or we can call it initial elevation. You can put it like this. This object might be moving and reach here. And the current position of this object is HF. We can represent it like this. HF. Now, students, the gravity is acting downward. Gravity is acting downward. It's always acting downward. Gravity is due to the weight of the object. That is a force, which is mass times gravity. Mass times gravity is the weight of the object. And the object is moving downward, a displacement of S. It moves a displacement of S. And we know that S and force are acting along the same direction. We could have a positive work done. Previously, we have discussed that work can be positive, negative, or zero. Therefore, in this case, work is defined as force dot S, or force times displacement times cosine of theta, where theta is the angle between the force and the displacement. In this case, the force is the weight of the object, which is mass times gravity, and the displacement here is S. S. And S can be interchangeably represented as what? S can be interchangeably represented as change in S, change in H. That means the difference between the final height and the initial height. We can have H final minus H initial. It's possible to represent it as delta H sometimes. Or if the initial height is 0, you can only use H. You can possibly use H. Therefore, it's possible to use S. It's possible to use change in H. If the initial condition is usually 0, we can possibly take as the final position is 0, we can take it as H. Therefore, the angle between the two quantities is 0. Theta is 0. Since the force is acting downward and the object is also moving downward, therefore theta can be taken as 0. Then let's try to find the work. Work is equals to force times displacement. The force is the weight of the object, which is mass times gravity, and the displacement S can be represented as change in H, times cosine of what? 0. Cosine of 0. Well, cos 0 gives us 1. Cos 0 gives us 1. Therefore, work can be given as m times g times change in h. Let's put it in this way, or it's also possible to use only h. This is the work done by gravity. Work done by gravity can be positive as the object is moving downward. As the object is moving upward, the work done might be negative. So work due to gravity and against gravity are positive and negative respectively. So upward gives us negative work done. Work done by gravity is negative. Why? Why it is negative? Because that the gravity is acting downward, but the object is moving upward. So they are 180 degrees. The angle between them is 180 degrees. And when the object is moving downward, work done by gravity is positive. Why it is positive? Because that work is acting downward, force is acting downward, the gravity is acting downward, the displacement is also acting downward. So it's possible to find work like this. So far we have tried to see about the work done by constant forces. We'll try to solve some problems. But now let's try to see about the work done by variable force. Students, can you mention the different types of, or can you mention at least an example for a variable force? For a variable force, a force which varies or depends with time. A force might be depends or varies with displacement, space and time. We can express it like that. Work done by variable force. Variable force. First, we should have to see about what does it mean by variable force. Previously, you have discussed that constant force is a force which is constant through time, which is constant through space or through position. Whenever there is a change of position, the force remains constant. Whenever there is a change of time, the force remains constant. But here, variable force might be changed due to the displacement or due to time. Therefore, variable force is a force which varies or changes due to position. One good example is the force exerted on elastic material, or it can be spring. One of the elastic material is a spring. So the force on spring is variable force. Force on spring is variable force. Variable force. That means the force, the applied force, varies due to position. I hope in lower grade you have learned about Hooke's law. Hooke's law states that for a given spring, let's take a spring here. Now, let's take a spring here with no load or applying any force. The spring might be like this. Now, if you exert a force here, when you exert a force, there is elongation. Change in x, we can call it change in x. That means x final, the final x minus the initial x, we can call it like this. So we can have the change in x due to the applied force. Whenever you apply force, the applied force and elongation or extension has a direct proportionality. That means this force has a direct correlation with the change of the position. F is represented as the spring constant K times change in X. We can possibly represent like this. Or sometimes change in X, if X initially is 0, it's possible to use only x. Change in x can be equivalently substituted as x. Therefore, this is what we call Hooke's law. F is equals to k times x. Now look, the force and displacement are correlated. Due to the change of the displacement or the elongation, there will be a variation on the applied force. So the applied force depends on the location or the position of the object. This is what we call variable force. So work done by such force can be mathematically represented using graphs. In previous concept, we have seen that work done by constant force can be represented on force displacement graph. Displacement graph. Look here, the force F, and here you'd have a displacement x, or in previous concept we have used it as s. In this case, if the force is constant, that means due to the change of the displacement, if there is no variation of a force, let's be here, let's say this is 0, we can take 1, 2, 3, let's say it might be 10 Newton. So whenever there is a change of displacement, the force remains constant. This is constant force. F is constant if the force is constant. The displacement might be here. This is s, or we can take it x. You can find area here. What does this area represent? Students, try this please. What is the area on force displacement represents? Well, note here, the force displacement graph, in force displacement graph, the area represents work. Area in force displacement graph represents work then. How? We know that work is the product of force and displacement. Therefore, from this to this represents the force. This is the force. The vertical line represents force. The horizontal line represents displacement. Therefore, force times displacement gives us, force is the length, you can take it width and length. Width and length, the product of width and length is area actually in length. But here the variables are not length. The vertical variable is force, the horizontal variable is displacement, and displacement is represented in meter and the force is represented in unit. So the product of these two gives us joule. Force times displacement gives us work, and that is the area. So area equivalently represents work. Students, can you determine the work due to this variable force? Can you determine the work done due to the variable force? We have already mentioned that force can be given as k times x under Hooke's law. Therefore, the force and displacement has a direct correlation. We can represent the work done by variable force on F displacement graph. Let's take the force. The vertical variable is force. The horizontal variable is displacement. We can take it as x. Usually for a spring and elastic materials, we take it as x. And here you have force F. The force and displacement has a direct proportionality. Force and displacement, they do have a direct proportionality. Whenever there is an increment, a linear increment of displacement, there is a linear increment of force. Therefore, force and displacement can be related like this. We can have such a linear relation. I hope you have learned this in your mathematics lesson. When two objects are linearly correlated, the graph becomes like this. Therefore, what is the work done what is the work done due to this graph? What is the work done due to this graph? Well, to determine this is horizontally represented as x, whereas this force F should be given as what? F is given like this. The average force can be represented as the initial. This variable force can be affected as the initial force. We can take it as average. Average means initial force plus the final force over 2. We can take it like this. So the average force can be given as what? Initially, this is 0, the initial force. We can possibly represent it as the final force over 2. We can have such a relation. Therefore, work can be given as force times displacement, or length times width in this case. The force is the average force times the displacement is x. The average force can be given as what? 1 over 2 F. We can equivalently represent it as 1 over 2 F. So 1 over 2 F times x. But the force F from Hooke's law can be given as k times x. Easily we can represent like this. Or in higher level, we do have an integral mathematical expression. We can solve for that, 1 over 2. Instead of this, we can have kx times x. Therefore, the work done by a variable force. Among the variable force, we just took only spring. So work done by the spring can be given as 1 over 2 k times x. In this case, we just took the initial x might be 0, but we can take it as the elongation, change in x. Okay, x or change in x square. This is how we determine the work done. We can possibly substitute here, change in x square. This is work done by variable force. Among the variable force, we just took spring force. So now, students, we can solve some problems. It's a time of activity. Let's try to solve some problems. Example, suppose a force is exerted on a spring as shown below. Let's take a spring here. So that this spring displaces from the initial location, let it be x initial, is 0. It's usually known as equilibrium position. Now it can be elongated till here. Let's take that x, the elongation, change in x, you can call it change in x, to be 2 centimeter. The spring constant, or known as stiffness, or sometimes known as force constant, be 10 Newton per meter. Let it be 10 Newton per meter. So what is the work done in displacing this spring a distance of 2 centimeter using external applied force? Well, the question is, what is the work done by the spring? What is the work done by the spring? So the spring always exerts against the applied force. Previously in Hooke's law, we have seen that force F can be represented as F k times x. This force and x has a direct relation. But in a spring, the spring exerts opposite to the direction of the applied force. So F and restoring force or force of the spring has opposite relation, so that they are negative. So work done by the spring can be given us due to the spring, the negative of 1 over 2 k times change in x square. We can possibly represent like this. Well, the negative of 1 over 2 k times change in x squared, 1 over 2, we can substitute k as 10. And instead of change in x, here you'd have 2 centimeter. You should have to convert it to standard unit because here the stiffness is Newton per meter. Therefore, the standard representation or the SI unit of length or extension is meter. We can have this as 2 times centi means 10 the power of minus 2 meter. We can put it here as 1 over 2, the negative. We don't have negative because it's acting oppositely. Negative 1 over 2, 10, and here you have 2 times 10 the power of minus 2, the whole square. So when we square this, it gives us 1 over 2, 10. This gives us 4 times 10 the power of minus 4. Therefore, we can eliminate this. 5 times 4 is 20. So 20 times 10 the power of minus 4 joule. Negative. So work is equals to, we can eliminate this 10, this 0, as minus 2 times 10 the power of minus 3 joule. Work can be negative, positive, or it can be 0. Therefore, this means work done by the spring is against the applied force, against the external applied force. That's why it becomes negative. ስለዚህ ተማሪዎች የዛሬውን ሌሰናችንን በዚሁ ጨርሰናል። እንግዲህ በሚቀጥለው አሁን የሰጠኋችሁን ጥያቄዎች ሰርታችሁ እንደምንገናኝ ተስፋ አድርጋለሁ። እስከዛ ኢንጆይ